So one of the things that I will use for some classes, some PowerPoint slides, but I'm not a big fan of them. So I encourage everybody to have the notebook ready and open for our classes and to be very proactive in the class and being, writing in the notebook together with me, asking questions. Hopefully we can make this as interactive as possible, okay? So that's the point, to make it fun for you guys. Okay, so we're gonna start looking into some basic Gen Chem concepts that some of you may know, but as I said, we want to go to make sure that we go over everything in details. So the one thing that I want to show here, you guys, is the structure of the atom. I'm looking for a draw right now. Give me 1 second. Okay, so can you guys see the screen now?
Yeah.
You should be able to see it, right? Correct. Okay. So, so let's talk about the structure of the atoms. Okay, so imagine this is an atom, um, and then let's say, sorry. So as you guys know, right in the center of the atom, we have the nucleus, and the nucleus, so right here. So here we have the nucleus. The nucleus is a very tiny portion of the atom as compared to the rest, right? Um, Anybody knows what can we find inside of the nucleus of an atom?
Neutral.
Pro-
Yes.
Protons,
And,
okay.
protons and neutrons.
Protons and neutrons, that is correct. Hmm. And in the rest, we find electrons, right? In that space. So the electrons, so most of the mass of the atom is just right here in the nucleus, and the volume is mostly occupied um, by electrons, okay? So electrons are all over here. So as you guys know, electrons are actually occupying shells here. So you have and they are in different energy levels. So they are what we call quantized. So that's also something that I want to show you here. Um, so I'm gonna write it. So we have different energy levels, level 1, 2, 3, and 4, right? And these energy levels are quantized, meaning that there is a certain number of energy, so it's not a continuous energy. Um, okay, let me see. Is that better? Okay, so thank you for that. So as you know, as I said, uh, an atom contains a very small nucleus in which we will find neutrons and protons. So what is the charge of protons? Everybody knows that protons are positively charged, correct? So that we know. I'm gonna say here plus. So everybody follow that. Mhm. Neutrons are neutral, right? So, and then the nucleus is surrounded by this space, and all this volume is occupied by electrons. And as we know, electrons are negatively charged. So I'm gonna write here now electrons are occupying the rest of the space, and they are negatively charged. Okay, so that's totally fine. Um, so we can define something called shells, and that says the probability of finding an electron in different regions of a space relative to the nucleus. Okay, and shells are quantized. So I'm gonna say here uh, we're gonna define what is a shell, and that's probability So around here we have like shells. I don't have, I was trying to draw it for you guys. I can try to say, let's see if I can do this. With colors. I can color code this. So, oh, 1 second. Okay, so I cannot, sorry. So shells are basically around here, okay? Everybody knows that. And this is, as I said, this level of energies are quantized, meaning that there is no continuous energy, but each shell has a specific energy values, okay? So the energy of electrons in this shell is quantized. That's important to keep in mind. So only very specific values of energies will be possible for electrons to have when they are in these shells. Um, there are several reasons why an atom keeps itself together. And, and the first is the electrostatic interaction between the negatively charged electrons and the positively charged protons, right? That's a factor. Second factor is obviously the repulsion in between the negative charge in between electrons. And the third, that is very important, is the wave-like nature of electrons, which I'm going to write over here because that is very important, and we will see a lot of that. So electrons have wave-like properties, which basically what it means is that they prefer to be delocalized, okay? So it's a pretty important concept, guys. And that brings me to the first definition that I want you guys to really understand: delocalization. So that's a really important word in organic chemistry and in chemistry in general, which is going to describe the spreading of electrons density over a large volume of space. Okay. So so I'm going to repeat again, just to make sure that everybody is following. Once again, we know the nucleus contains neutrons and protons. Around the nucleus, we have electrons. Electrons will be in shells. These shells has energy which is quantized, right? And the reasons to keep this together, number one is the attraction, electrostatic attraction between the negatively charged electrons and the positively charged protons. Second thing that plays a role on the size of an atom is the repulsion in between electrons. They are negatively charged, so obviously there's going to be repulsion between this negative charge. And the third thing, which is very important, is the wave-like properties of electrons, meaning that they prefer to be delocalized. So what I mean by that is if you have two electrons in the first shell, I don't want you guys to be thinking about one electron being here and one electron being there. So let's say I'm going to draw a shell here. Um, Imagine this is, I'm going to write here, this is shell number one, just to, as an example, okay? So shell number one will have two electrons, and we will see about that rule now. Because electrons have wave-like properties, I don't want you guys to ever think from now on that we have one electron in this area, another one over here. No. So we are going to talk about electron density because electrons prefer to be delocalized. And we are calling delocalization as spreading the electron density over a large volume of space, meaning that we know that we have electron density around this area over here. We don't have one electron, one here, another electron, and the rest is empty. No, there is electron density all over this shell, okay? Because electrons are delocalized. And the concept of delocalization, once again, having electron density spread over a large volume of space, That is very important to understand a lot of things that we are going to be going over later on. So Kevin asked, can you please repeat the first point? So Kevin, the first point that I was talking and when I write in here is attraction between protons which are positively charged and electrons which are negatively charged. Okay. Point number two is repulsion between electrons which are negatively charged. And point number three, electrons are delocalized. Okay. It's a very important idea of, and this is basic, but it's really critical because, again, we're talking about an atom now, but then later on, when we talk about molecules, this will become even more relevant to understand all these concepts. Okay. So we're talking about electrons being in shells around the nucleus, and those electrons are always delocalized. So we're going to talk about electron density mostly. Okay. All right. Any other questions? Okay. So in each shell, okay, they are going to have a different quantum number, and each shell will contain a different number of electrons. Okay. So uh, the maximum number of electrons that a shell can have is equal to 2n squared. Okay. And I'm gonna emphasize here that's the maximum number. It doesn't mean that it has to have always that number of electrons. That's the maximum number of electrons, okay, that a shell can hold. Is 2n squared, where n is the number of the shell, the quantum number of the shell. So for shell number one, how many electrons can we expect to have in shell number one? Two electrons, beautiful. Max, okay. Shell number two, how many electrons for shell number two? 8, beautiful. And then what about shell number three, the third shell? 18 electrons maximum. That's beautiful. Okay, so that's also important to keep in mind. Maximum number of electrons that we can hold in one shell. Okay. Now, obviously, the electrons that are closer to the nucleus, okay, those electrons are strongly attracted because they are very close to the positively charged protons. So the farther the electrons are from the nuclei, the less tightly held they will be, right? So I'm going to also now take this opportunity to define something that is very important in organic chemistry, and it's called electronegativity. And we are going to define that as the power of attraction of the electron for the electrons in the most outer shell. Okay, so that's something we're going to practice a lot, but I wanted to introduce a concept from now. So once again, the closer uh, the electrons to the nucleus, the more strongly attracted they will be because obviously they're closer to the protons, right? And the opposite. So we can define electronegativity of the power of attraction of an atom by its outer shell electrons, okay, of the valence shell. That's what you also should know from Gen Chem. So if the outer shell if the most outer shell is shell number 3 in one atom, in the second atom it's shell number 5, then obviously uh, shell number 3, that atom with shell number 3 is going to be more electronegative because it's going to be attracting those electrons that are farther away from the nuclei strongly. Okay, so we were going to have time to go over this in details, but electronegativity is a very important concept to understand a lot of things in chemistry and in organic chemistry in particular. All right, so another thing that I also wanted to go over here is uh, now what happens within a shell. So shells are subdivided, but are divided in subshells. Okay, and those subshells are designated by letters. In this case, S, P, D, and F. So remember, once again, you can calculate what's the maximum number of electrons that each shell can hold, and then each of these shells is going to be subdivided in subshells. Okay, we're going to call these subshells orbitals. Okay, and let's define what is an orbital. That's another very important concept uh, in chemistry. So we can define an orbital as a region in space that can hold 2 electrons. Okay, and it does have specific quantized energy. So point being is, and this is also crucial, as I said, the maximum number of electrons that an orbital can hold is always obviously going to be 2 electrons. Okay. So once again, around the nucleus, we're going to have shells. Each shell can have a maximum number of electrons, and within each shell, we have subshells. And these subshells, we're going to call them orbitals. Okay, and the maximum number of electrons that an orbital can hold is 2 electrons. Okay, so according to this, in the first shell, in shell number 1, how many orbitals are we expecting to have in shell number 1? What's the maximum number of electrons that we can have on shell number 1? 2 electrons, right? Good. So if we can have a maximum of 2 electrons, how many orbitals do we have in shell number 1? 1 orbital, right? So, and that orbital, we are going to call it 1s. There is an explanation. So it's a 1s orbital. That's what we're going to call it. 2 electrons max. And the shape of a 1s orbital is an sphere. And that's something also we will see later on, but in organic, we also go over this. So S stands for sphere. Okay, that's the reason why. And you may ask yourself, why is this 1s orbital and a sphere? There is a lot of science called quantum mechanics behind this. And this is the result of plotting some math equations, and that's where the sphere comes from. We can talk a little bit more about that when we go over molecular orbitals, but just to give you a brief explanation so you understand that this shape is not coming out of nowhere. So it's coming from plotting math equations uh, from quantum mechanics. Okay. So in the second shell, how many orbitals should we expect to have in shell number 2? So shell number 2, you can have a maximum of 8 electrons, right? Yes or no? What's the maximum number of electrons that we can expect for shell number 2? 8 electrons. Good. And so if we can have 8 electrons, guys, and this is so important in organic, you will see what later. What is the maximum number of orbitals that we can have in actually not the maximum, what's the number of orbitals we will have in shell number 2? 4 orbitals. Okay, so one orbital is gonna be s, and 3 are gonna be p. I'm gonna call them px, py, and pz. Okay, so once again, shell number 1 can hold a maximum of 2 electrons. So that's one orbital, and we are going to call this orbital 1s, which is an sphere. Shell number 2, 2n squared of shell number 2, that's 8, right? We concluded that here. So if we can hold a maximum of 8 electrons in shell number 2, we will have then 4 orbitals, because we know that one orbital can hold a maximum of 2 electrons. And these 4 orbitals are going to be 1s and 3 2p orbitals. So let's get a little deeper into this. Remember how I said that orbitals are regions in space that can hold 2 electrons, and they have a specific quantized energy. It's important, okay? So the s orbital is slightly less energetic as compared to the p orbitals, which are higher in energy than the s. Now the 3p orbitals they have the same energy. Let me do this row correct. Okay, so the 2s orbital is going to be, as I said, slightly less energetic as compared to the p. The 3p orbitals, they all have higher energy as compared to the s, and they have the same level of energy between them. So we said that they are degenerate orbitals. I'm going to write it over here, meaning that they have exactly the same level of energy. Okay, so now uh, the next question here is what is the shape? So we know that the 2s orbital, once again, S is a sphere, but the 2s orbital is going to look like this. It's slightly different to the 1s because it has a node. I'll go over what that is now. And then let me show what a p orbital is. So here is a p orbital. Okay, so this is a p orbital. That's the shape of a p orbital. Okay, so it's a lobe, as you can see here. So a couple of things that I want to emphasize in regards to the p orbitals. The shading here, guys, some of these things might be now a little bit confusing, so I'll be happy to answer any questions that you might have, but I'm gonna say this once again slowly. So remember once again, electrons are delocalized, okay? Meaning that, for example, this orbital, there is electron density inside this sphere, okay? Around the entire sphere inside, every single point on a space here, there is electron density because electrons are delocalized, okay? When we talk about a p orbital, we have two lobes. And there is electron density here, and there is electron density here. I shaded one of them, and the other one is not shaded. It does not mean that there is electron density in one and none in the other one. No. So the shading refers, and I'm going to write it over here to avoid any confusion. I'm sorry. In different textbooks, you will find different colors for the shades, okay? So the shading means simply something that we call the sign of the wave function. So it's a little bit advanced of a concept for you guys now. So remember how I just said that the electrons have wave-like properties over here, right? That is very important because that's all the foundation for quantum mechanics. So this wave, the wave, and we will see that later in the semester. When you think about a wave, you can think about the wave of when you're plugging a guitar or in the sea, the waves, right? They have positive and negative signs, okay, because they oscillate, and that's what it's referring this. So you don't really have to have a full understanding of what is the sign positive and negative. It doesn't really matter, okay? But what is important, and I want you guys to, let's say this could be a positive, depending on the textbook, okay? Doesn't matter because electron density is going to be the square of this. But at the end of the day, what I want you guys to keep in the take-home message for now is when you see a p orbital shaded, do not think that the electron density is only in the shaded area. No, it's in both. Okay, equal electron density in both lobes. Now, what is the electron density right here? Anybody knows? What would be the electron density right here at the point where both lobes are together? So the electron density there is going to be 0. So we call this a node, and it's an area of 0 electron density. And now it makes a lot more, should make a lot more sense to you because whenever you have an area of 0 electron density, there is a change in the sign of the wave function. That's why you have two opposite signs of the wave function here. Okay, so whenever you see a p orbital, the p orbital has a lobe, the shape is a lobe, okay, like exactly as is shown in this picture. There will be electron density above and below. And there is going to be a point in between both lobes we will call the node. And in exactly at that point in the node, that's an area of 0 electron density. And that's why you have two different signs of the wave function, up and back, up and down, sorry, okay? Also, continuing with the 3D picture of a p orbital. I'm gonna move it over here because I'm gonna do something else. Guys, if you have questions, feel free to interrupt me or ask, okay? I'll be happy to stop. Let me see somebody. Okay, can I explain degenerate? So degenerate now are orbitals having the same level of energy, okay? So we have three p orbitals here, and you can see how, and I didn't, I forgot to draw something here to make it really perfect. So this is an energy diagram, okay? Apologize for that. I mean, I assume you guys knew, but just in case. So we're talking about energy diagram, okay? So degenerate means that we have three p orbitals. So as I said, in shell number 2, we have 4 orbitals maximum because you can find 8 electrons. So one of these 4 orbitals is 1s, which we know is a sphere. You will find electron density inside that sphere everywhere. And then we have 3 p orbitals, x, y, and z. And these 3 p orbitals have exactly the same energy level. So we call them degenerate orbitals because they have the same energy levels. The 3p are slightly more energetic than the 2s. Is that clear now? Okay. So we were focusing, going back here to from on the shape of a p orbital, which we discussed is a lobe as it's shown here. With electron density above and below, there is a node right here in the center in between both lobes, and that is an area of 0 electron density. And whenever you have a node, you're going to have a change in the sign of the wave function, and that's what they refer in textbooks with the shading or the colors. Okay, very important. You will find electron density above and below, always both. So also wanted to show you in regards to this, I'll see if I can draw something here. So for any p orbital, you also will have something we call a nodal plane, which I'm going to try to draw here now. Okay, let me see, I think, okay, so since the p orbital has slightly more energy than the s orbital, with the electrons being the p orbital be slightly further away from the nucleus, yes, they will. Not a huge difference, okay? The more significant difference will be in between shells, okay? What does the positive next to the shading of the lobe means? Exactly, so thank you, Iman. The sign of the wave function is positive, okay? That's what it means. Because I'm emphasizing that when you guys read, and in the next semester, when you, and even now in organic, in Gen Chem, when you see these pictures of p orbitals, you'll see different colors. Some books use different shading, and a lot of students, especially at first, tend to think that there is electrons here, and because this is empty, nothing here. No, there is electron density in both lobes, equal electron density. It's just a sign of the wave function. The only thing that is different. And what I said here, I drew a plane here, right? And that plane is across the node. So, and we call this a nodal plane. And that's once again a plane where we have 0 electron density. Okay. So in every single p orbital, you'll have a lobe with a node and a nodal plane. Okay. So it's a big difference in between a p orbital and an s orbital, as you can see. Okay, the shape of the orbital is different, meaning that the electron density areas will be different. That's important. Now we have 3 p orbitals. I say we had x through y and z. So these 3 p orbitals are orthogonal to one another, which means that they are forming in 90-degree angles in between them. I'm gonna try to use color codes to show you guys that what I mean by that. Okay, so this is also extremely important. I said there are 3 p orbitals, okay, and they are orthogonal to one another. In this context, orthogonal, and I'm gonna write it just in case. So orthogonal p orbitals meaning that it's 90-degree angles.
That shows 2px, 2py, and 2pz right there.
Correct. Mm-hmm.
Where would the 2s be? Smack dab in the middle?
The 2s is a subshell. It's in a different one. Okay. Below these three, you have the sphere. Okay.
Below it, heard. What do you mean below it?
So below in energy. So remember we are talking about
Below.
shell number two, right?
Let's see.
So shell number two is the second shell here. And in that shell, we have two subshells, S and P, very close in energy to one another. Okay. The S is slightly below in energy than the P, and this as in a sphere, it can only hold 2 electrons. Okay. Was that
I
clear
just,
or not?
well, I just don't know where you'd like if you're fitting the 3 dumbbells on the shell. I just don't know
Mm-hmm.
where you'd put the 2s if it's all on the second shell.
All out on the second shell, exactly. So it's like I can do this. I'm just giving you the three. So when I draw it like this, it's just a schematic representation, but this is uh, the 3D draw, right? So you will have, this would be how they will look. Okay.
I see it. It's just like, is it all like within the shell, or is that
Exactly.
those are
All
all
is all is in
places,
shell number two.
and that's all places where it can potentially be.
Yeah. So these two are very close in energy, whereas we'll see now when we do the electronic configuration of one atom. But the point is that in shell number two, you have 1s and 3p, and they will look like this. Okay.
Heard. All right.
All right. So, uh, okay, the sign of the wave function again. Um, that's a little bit advanced, but I'll try to make it simpler for you. So here is what happens. As I said, the electrons have wave-like properties. Okay. So based on that, making an analogy with photons from light, and because photons from lights, they also have wave-like properties, and using math equations for waves, and that's a very complex quantum mechanics concept that, uh, based on that, a very prominent scientist called Schrodinger uh, came up with equations that describes orbitals in atoms based on the wave-like properties of these electrons. And the solution to these equations are these orbitals, and that's why they have these shapes, okay? And in these solutions, some solutions are positive and some are negative, so that's what it means. Um, we will see some more of that when we talk about molecular orbitals, but as I said before, so you should know this refers to the sign of the wave function, but most importantly, especially right now, please always remember that it does not mean that there is electron density only in one lobe. Not at all. There is equal electron density in both lobes, even though they have different colors or whatever uh, terminology you find in any textbook out there. Okay. So so you can continue and you will do this for uh, shell number three. Then you have 3s, one 3s orbital, three p orbitals, and five d orbitals. That's we will see more about that in Chem. But I'm gonna stop in shell number two for several reasons. The number one reason is because in organic chemistry, it's the chemistry of the carbon. Okay, so I'm gonna write it over here too. Organic chemistry is the chemistry of carbon compounds. Okay, uh, so we are alive because of orgochem. literally. So all the molecules in your body, they are organic compounds. I mean, you have also obviously inorganic molecules, but the molecules that are making up your body, proteins, lipids, you know, they are all organic compounds. And organic compounds, the backbone of these molecules is the carbon atom, and the carbon atom is so relevant because it has this ability of binding to other atoms, carbon atoms, and forming these long chains. And that's why you will find 95% of the compounds that we find in nature, they are organic. That's why we have a class just for organic chemistry, right? So the point is that we focus in a lot on carbon, and also we have oxygen atoms in organic molecules. There is also sulfur, phosphorus. It's more, obviously hydrogen is the other big deal, right? Mhm. But so carbon is on the periodic table, and I'm gonna write over here. Carbon is in group 4 and period number 2. Uh, have you guys studied the periodic table in general chemistry or one? You should, right? I haven't taught Gen Chem ever, so okay, good. The trends and everything, beautiful. So, so you guys know at this point, the group number equals what in the periodic table? What information does the group number give you? If you see carbon is in group 4, what is that telling you? The number of valence electrons, right? So valence electrons. And what about the row?
It tells us if it's like an alkaline or like no, actually it's
Not
group
general. The number of the valence shell. So one is the valence electrons, and the second one is the valence. And this is very important, guys. Shell. Okay. So when you're talking about carbon being in group 4, shell number 2, we know that carbon has 4 valence electrons, and the valence electrons are located in shell number 2. Correct? Everybody agrees on that?
Yeah.
Yes, right? Now, my question is, and this is, you will see how I'm coming with why I'm going over this. So group equals valence electrons, period equals valence shells. So I'm gonna say for carbon, which is a very important element for us, 4 valence electrons in shell. Okay. Okay. So now my question is, how many orbitals do we have in shell number 2?
2,
Nope. Total. What's the total number of orbitals that we can find in shell number 2?
4.
4 orbitals. Okay, in
Oh,
shell
I
number
see.
2, we also have 4 orbitals, correct? And therefore, guys, and this is very relevant, okay? What is the maximum number of bonds that carbon can potentially have?
4.
4, okay? So you never ever draw a carbon with more than 4 bonds. And now you should understand why. Because the valence shell of carbon is shell number 2, and in shell number 2 there are only 4 orbitals. So the maximum number of bonds is going to be 4. You could find a carbon with less than 4 bonds. You will discuss that in organic chemistry. But never ever you can find a carbon with 5 bonds. And when you draw a carbon with 5 bonds, it's something really awful. Because as I said, carbon is the element that we most care about. Okay. So it's very important for me, particularly you guys going into organic chemistry, understanding not only that carbon has a maximum of 4 bonds, but understanding exactly why. And it is because the valence shell of carbon is shell number 2.
So when
Okay.
we did the little air, could you scroll up just a little bit? So in that little energy diagram you have, so it'd be one arrow in each little thingy.
We'll see that later because it depends.
Or-
It's not exactly that. We'll see that right now. Okay, so okay, so now that we got a thorough understanding of bonding, not bonding, sorry, of what is an atom and electrons and shells and orbitals and electronegativity and all these things. So the next is I'm going to remind you, and we're going to practice very briefly here how to do the electron configuration of atoms, which is something that is very important too, because we must know how to do that really well. Okay. So why do we care about? Well, it's very relevant because that's the description, right, of what kind of orbitals the electrons of these atoms will be occupying. And we really care about that because that's going to determine reactivity of these atoms and everything later on. So we really need to got a solid understanding of this. Okay. So in theory, one atom can have multiple number of electronic configurations, but we're only going to focus on, for now, in something we call ground state configuration. Okay. Which is the lowest energy electron configuration for an atom of molecule. That's why we care about this. Okay, that's the ground state configuration.
And instead of lower, you meant lowest, right?
What? No, lower energy. We'll see what that is now. Lower energy configuration. Okay, so let's take an example of the atom of carbon, and then I'm gonna discuss the rules that you must follow to do the electron configuration of any atom in the periodic table. All right, so what is the atomic number of carbon? Nope. Okay, 6. Any other answer? What's the atomic number of carbon, guys? Is 6. Guys, what is the difference in between every atom in the periodic table? What do they differ in? What do they have different to one another? Each atom in the periodic table. The number of protons, right? That's correct. So if we're talking about atoms that are neutral, right? So carbon, the atomic number is 6, meaning that it has 6 protons. How many electrons should carbon have? If it has 6 protons and it's neutral, carbon must have 6 electrons, right? Okay, so in the first level, how many electrons in the first shell can I have? What's the maximum number? 2, right? So I'm gonna throw 2 here. So we always fill up energy levels in from bottom to top, meaning from lower energy to higher energy, right? We know that each orbital can only hold a maximum of 2 electrons. So the 1s orbital, okay, which is shell number 1, will be having 2 electrons. Now we go to the next shell. In the next shell we have the 2s, and then we have the 3 2p orbitals. So you can see I'm drawing the, let me make sure that everything is properly drawn here. Okay, so showing these two closer in energy and showing the difference in between this and the 1s, which is below. Okay, I'm gonna say 2px. Okay, yep. Draw this slightly lower just to, for the simplicity of the drawing. Okay. All right, so we have 3 2p and 1s, 2s, I'm sorry. So that's 4 orbitals for shell number 2, so everything is correct. How many electrons should I place in shell number 2? 4, right? Because the total is 6 and I already had 2. So if I have to place 4, I'm gonna fill up my lowest energy next, which is gonna be the 2x, the 2s. So I'm gonna go ahead and fill that with 1 electron here and another one. I'm drawing the electrons like this because that's what we call spin pairs. So spin is the nuclear magnetic property of electrons that I guess you should have learned. Yes, C is the atomic number, Michael. So that's what these two pointing up and down means, the opposite spins. And you always have 2 electrons in an orbitals and they will have opposite spins. So we have 2, 4, and now we need another 2 to complete 6, okay? So guys, this is once again the rules to complete the electron configuration of atoms. And that's gonna be from bottom to top, from lower energy to higher energy levels, okay? And then once we get into orbitals with the same energy level, so degenerate orbitals, we place 1 electron in each. So we're gonna have 1 electron here and 1 electron here. Okay, so the electronic configuration of carbon is gonna be 1s2, 2s2, 2p2. Okay, it's very relevant because again, we are gonna be using this a lot later on, okay? Okay, so what about, let's do, I wanna do also oxygen.
But d orbitals are the outlier when you have 5, right?
No, here we don't need, the orbitals are on shell number 3, and we don't need to go to shell 3 here, right?
Yeah.
Because shell 2 is already completed.
You know what I'm talking about though when it comes to the d orbitals, the rule about the 5 and the 9 or the something like that.
Then you have the different order and everything. Yes. Um, you will see that more on Gen Chem. I'm here more focused on, as I said, period number 2. So what about oxygen, guys? What's the atomic number of oxygen? 8. So if 8 is the atomic number of oxygen, that means that we have 8 protons, and then we have 8 electrons. So if we have 8 electrons, we just need to add to compare carbon. So we have 2, 4, 5, 6. We need to add 2 more. So I'm going to add 1 here. Once again, we complete the degenerate orbitals first, and then 1 over here. Okay, 2, 4, 5, 6, 7, 8.
Wouldn't
So
that
guys,
be 2p4 for oxygen?
2s2, 2p4.
Oh, it's just written down wrong.
Okay, and I also want to do nitrogen because nitrogen is in the second period of the periodic table and is in group 5, oxygen is in group 6. So, anybody remember the atomic number of nitrogen?
I think 7.
7. Okay, so obviously, so as I said, carbon is in group 4, 4 electrons in the valence shell. Nitrogen is in group 5, 5 electrons in the valence shell. Oxygen is in group 6, 6 electrons in the valence shell. So guys, something else that I want to show you here is, as I said, the maximum number of bonds is 7. So 2, 4, 5, 6, 7. This is 2p6. Is my sorry.
No, the oxygen's
I'm sorry,
right.
sorry, sorry.
It's the
Yeah, yeah,
nitrogen that's wrong.
yeah. Yeah, I'm sorry. I'm sorry, sorry, sorry.
No worries, no
Okay.
worries, I guess.
Okay.
I'm sorry, I have a question.
Go ahead.
Isn't it nitrogen SP, the last one, 2p3 instead of 2p5?
Yes. Yeah. Okay, so you just increase one electron in the valence shell for each one of them. So guys, what I want to show you from here is, especially for these two, because again, we're gonna see this in details, much more in details later on. But this is a kind of a good reminder of Chencam. So you see how in oxygen here, in the valence shell, 2 orbitals already have 2 electrons, okay? So it only has 1 vacant here and 1 vacant here. So how many bonds do you think oxygen can form to be neutral?
2.
So obviously 2 bonds. So that's where you can understand that an oxygen with 2 bonds is a neutral oxygen. And we will see now hybridization and everything later on, which is a totally different thing. But for now, I want you guys to at least look into, make sure that you really understand this, okay? 1 second. So there is only 2 vacant, so now remember, Rachel, the question was how many bonds can an oxygen form to be neutral, right? So 2 orbitals are already full. That's going to be lone pairs. So it can only accept 1 electron here and 1 electron here. So it can only form 2 bonds to be neutral. Doesn't mean that you cannot have an oxygen with 3 bonds and so forth, okay? What about nitrogen? How many bonds would you expect in neutral nitrogen? Right, 3. Okay, so we're going to go back to this because once we look into bonding theories, this is going to be important. I'm sorry. But I want to also, now that we described electronegativity, let me see if I can find, I'm sorry, a periodic table here. So when you talk about electronegativity, and as I define electronegativity as the power of attraction by the electrons on the in the valence shell, right? What happened in a period with electronegativity from left to right? So let's say, so as I said, carbon is group 4, nitrogen is group 5, and oxygen is group 6, right? So when we go from 4 to 6 in the same row of the periodic table, the electronegativity increases. That's correct. And what happened here is, anybody knows why does it increase? So it increases from left to right.
Because there's more electrons within the same shell.
And there are, well, and there are more protons too. So the important thing is in the same period, in the same row, guys, remember the valence shell is the same. In this case, it's shell number 2. So the size for the shell in theory should be very similar. So not a big difference in size because we're talking about the same shell, right? Now the number of protons and electrons is increasing, the attraction is increasing, and therefore that's why when you go from left to right, the atomic radius decreases and electronegativity increases. Okay, that's a very important thing to keep in mind. And what happened now with electronegativity in
Can
a
you
group?
just repeat what you just said like 5 seconds ago?
Yes. So
In a
so we
period.
go from left to right. So I'm gonna say here, and I'm gonna color code this so you guys can follow what I'm saying. Okay. So from left to right, the valence shell is the same. In the same period of the periodic table, we are talking about the same valence shell. Okay. Uh, so what happened is the size is not dramatically changing because we are talking about the same valence shell. Now, from left to right, the number of proton increases, the number of electrons increases, so the attraction is stronger. Therefore, that makes the atom slightly smaller, and that makes the electrons to be closer to the nuclei. So that's why electronegativity from left to right increases. Okay. In a group,
So it makes the atom smaller.
slightly smaller.
All right. So there's
And then
stronger attraction. So it makes the atom smaller, and there's more attraction between the electrons and protons because there's more.
exactly because they are closer to one another. So in a group from top to bottom, what happened to electronegativity? So it decreases as you go down, correct?
Okay.
Why is that?
Well, you have the same number of electrons, but the valence shell, the higher up you are, it's smaller valence shell or closer to the nucleus.
Exactly. So you go from top to bottom in the same group. We are talking about the size is increasing substantially because every atom you go down, it has an extra shell, right? Therefore, you're increasing the size. And we are talking defining electronegativity as the power of attraction by the electrons in the outermost shell, then obviously the farther the electrons will be, the less electronegative the atom will be. So that's why fluorine is the most electronegative atom of the periodic table because it's all the way to the right and all the way to the top in group number 7. Okay. If you check into different textbooks, you will see that electronegativity can actually be quantified, and um, and that's important because later on we can talk about ionization of atoms and things like that. So the point is that scientists have done experiments to quantify uh, electronegativity value, and that those numbers are extremely important to make predictions in reactions. So with this information in mind, what I want to do is to also briefly go over you uh, with the Lewis model of bonding, which is also something that is important. And so I'm gonna write it over here. Okay, I'm gonna make a new. Let me open a new page here. Sorry. So we're gonna talk about the Lewis model of bonding, uh, and that's also it's gonna take us to what we call the octet rule, which is something that's gonna also help us to define bonding in chemistry and particularly in organic molecules. So I'm gonna reshape this pretty quickly. Okay, so we're gonna talk about Lewis. I'm gonna expand now. 1 second, okay? Okay, so so as I said, we cared about the outer shell of electrons or the valence electrons because guys, those electrons are the less tightly held by any atom. So those are the electrons that will be participating in reactions. Okay, so that's why we care so much about them. So and those the valence shell, when you have empty orbitals in the valence shell, those orbitals will be the ones used to receive electrons to form bondings, or the electrons in the valence shells are the ones that are given for bonding to another atom. So that's why we care so much about the valence electrons and the valence shell, because when we think once again about reactions, those are the electrons and the shells involved in those reactions. So based on this, to understand the Lewis model of bonding, the one thing that I want you guys to understand and know is what we call a symbolism that we call the Lewis dot structures. So Lewis dot structures, very simple. Okay, so Lewis dot structures, what they actually means is that is a symbolism, as I said, named after an American chemist, uh, Gilbert Lewis, who was the one who actually proposed this model. So in the Lewis dot structure, the symbol of the element, let's say, for example, I'm gonna say sodium, okay? Sodium is in group number 1. So the symbol of the element is gonna be showing the core electrons of that atom or element. And then we are gonna use dots to show the valence electrons, okay? So sodium is in group 1. How many electrons do we have in the valence shell?
1.
1, right? So if we're gonna draw the Lewis structure of sodium, then we're gonna just put a dot here, and that would be the Lewis structure of sodium, okay? If we think about oxygen, for example, okay, how many electrons in the valence shell of oxygen?
6.
So we have 6. So oxygen is in group number 6. So it has 6 electrons in the valence shell. So that's going to be 6 dots. I'm going to draw them in a specific way, and you kind of will accept it for now because we will have to go over molecular orbital theory to understand why I'm doing this. If you do this, you can do the 6 dots for now, however you like. Okay, it's not. I'm drawing them like this because it's more correct. Uh, but in any case, and let's say if you think about an atom like, for example, fluorine, which has 7 electrons in the valence shell. We're talking about now 7 dots. So that could be the Lewis structure for every atom of a periodic table. So that's very simple to do. The point of this is that now you can also draw Lewis structures for organic molecules, and we will see that in probably in the next class. Okay. So to begin with, so for now, according to the Lewis model of bonding, once you know the Lewis structure, then we can think about how do atoms interact with one another to form a chemical bond. And according to the Lewis model, I'm gonna write it over here. So atoms interact in such way that each participating atom will complete an outer shell electron configuration. Pretty much because once again I'm focusing on carbon, an element of the second row of the periodic table, although you can apply this to some others. They are completing 8 electrons in the valence shell. So atoms interact in such ways that each participating atom will acquire so what does 9 mean? Uh, I'm, okay, I'm gonna continue right here anyways. 8 electrons in the valence shell, or a complete. I'm gonna say to be need more specific, a complete outer shell electron configuration. Okay, so that's a Lewis model of bonding, and that is important because it can explain a lot of the reactions in chemistry in general, not only in organic but also in inorganic chemistry. And it can also make a prediction of uh, what kind of bonding can be formed between two atoms when they are interacting with one another. Okay, so let me show you then here an example. Let's say you have an atom of sodium. Sorry. Interacting with an atom of fluorine. So if we bring these two together, and what I'm gonna do also, guys, is to show you here the electron configuration. So the atomic number of sodium is 11. So let's do the electron configuration of sodium. 1s2. I'm gonna write atomic number here for those of you. Mhm. Okay, so 1s2, 2s2, 2p6. What else? What am I missing here? So 1s2, 2s2, 6,
S1.
and 3s1. So that's
The
11.
3-1B couple because it's in a whole new shell.
So, and then fluorine is, and we can only draw the valence shell if you want to. Fluorine is in group 7. So atomic number is 9. Okay. So I'm going to move this to the side so you guys can see this better. And this would be now 1s2, 2s2, 2p5. So you can see, guys, how if you get these two atoms together, so I'm going to use half, and this is going to be something that I'm going to do for the first time in the class. We are going to be using this a lot. So I'm using half an arrow here. That's the symbolism. Guys, we're going to, and the most important skill that you're going to use in organic chemistry is the curved arrow symbolism, okay? This is just, a very basic example of how to show this. But what I'm showing here is that if sodium donates 1 electron to fluorine, then sodium is going to be left with a complete octet in the valence shell right here. And fluorine is going to also complete an octet in the valence shell, which means that they both will complete an octet in the valence shell, and they both will have electron configuration similar to that um, of the noble gases. Okay, so that brings you to, and that's what I mean about by the curved arrow. So the arrow always, whenever you use a curved arrow for a reaction, and this is something again we're going to repeat a lot, so many times in the semester. So the arrow is always departing from the source of electron. In this case, I'm showing this electron is going to go over chlorine. So if sodium is losing 1 electron, what's going to be the charge of sodium now?
Positive.
It's going to be positive because it's losing 1 electron, right? So, and then if fluorine is accepting 1 electron, obviously, then it will become negative, okay? So what's happening in this reaction is uh, 1 electron is being transferred from sodium to fluorine. So there is a full transfer of electron. That's why sodium is becoming into sodium plus, which is a cation. And fluorine is becoming into fluorine minus fluoride, which is an anion. So we are talking about ions being formed, right? So because, and this is what we call an ionic bond. So definition of ionic bond, there is a transfer of electrons from the lowest electronegative atom to the highest electronegative atom. That's what we define by definition an ionic bond, okay? So when you have an ionic bond, usually ionic bonds are formed when there is a significant difference in electronegativity in between both atoms that are interacting. Usually the difference in electronegativity, we will see about this some more next class, is larger than 2.5 according to the Linus-Pauling scale of electronegativity, which you can find in many textbooks, okay? So definition here is according to
So
Lewis
an,
model of bonding. Let me finish.
ionic bond, an ionic
Let me
bond has a difference in electronegativity of at least 2.5, right?
Yes. So in the Lewis model of bonding, when two atoms are coming together, okay, They are reacting in such a way that both atoms are completing 8 electrons in the valence shell, particularly for, or at least if not 8, a complete outer shell. I'm using 8 because I'm focusing on elements of the second row, okay? Now, if these two elements have a highly significant difference in electronegativity, larger than 2.5, there will be a transfer of electron from the lowest electronegative atom to the highest electronegative atom, and in that case, we are talking about now forming ions, so cations and anions. And now in that case, we are talking about ionic bonds, okay? Ionic bonds are the strongest bonds of the out there because you have two electrical charges opposite to one another, positive and negative, which are attracting to one another very strongly. That's why, for example, if you try to melt table salt at home, you will never be able to because it's an ionic compound. So the interaction in between the atoms is so strong that you really need to supply a lot of energy to break this interaction down. Okay, that's a full transfer of electrons. And once again, uh, when you have two electrons that are quite significant in difference in electronegativity, that's what happens. Now, when you have another different kind of bond, and I'm gonna say this briefly because we are finishing and we will get into this more in details in the next class. When we talk about something like this, let's say a bond in between carbon and hydrogen, okay? So I'm gonna show you here the values for electronegativities. For carbon, the electronegativity is 2.5. The value of the Linus Pauling scale, and for hydrogen is 2.1. Okay. When you have a bond forming between two atoms with small difference in electronegativity, okay, we are talking about a covalent bond. And in a covalent bond, electrons are shared between the atoms. There is no transfer of electrons whatsoever. The electrons are shared in between both of them. Now, we
What's
will
the
see in the next
margin?
class, let me finish. We will see in the next class different types of covalent bonds because there are polar covalent bonds, non-polar covalent bonds. So that will depend on the difference in electronegativity, how polarized these bonds will be, meaning these electrons will be closer to which atom and how much closer they will be. But the main difference in between an ionic bond and a covalent bond, and that's why it's so important because in organic molecules, they all have covalent bonds. Carbon and hydrogen, and these are the two most common atoms in organic molecules, they have a very small difference in electronegativity between them. That's why they can form non-polar covalent bonds, which are obviously much more stable than ionic in the sense of reactivity, that polar covalent bonds because there is no charge whatsoever being formed, okay? So we will continue discussing about Lewis model of bonding in the next class, and we will get some more into hopefully some other bonding theories that are much more relevant. Uh, with that in mind, I'm going to stop recording. If you guys have questions, I'll be happy to answer.